Hello, hello. If you can share your screen and okay, try to move your pointer. Okay, amazing. So the last speaker of the workshop and of this second session is Anna Banks from Cambridge, who's going to talk about energy transport by dark matter scattering in stars. So it's definitely on point compared to the other topics that we discussed this morning. So whenever you're ready.
Fantastic. Well, thanks very much for inviting me here today. So today I'm going to be talking about some work which was done in collaboration mainly with Aaron Vincent and Pat Scott. So I think after all of the talks this week, we are all probably in agreement that the motivation to pursue whatever the fundamental nature and properties of this elusive dark matter is pretty unquestionable. But as we've seen from the wide variety of talks on this week, how and where best to look for this dark matter is pretty unclear. Now, terrestrial-based direct detection experiments, which look for dark matter collisions with heavy atoms, have always been a favoured approach, but they're of course yet to yield a discovery. However, all is not lost. It turns out we actually have an entirely complementary direct detection experiment on our doorstep that we are yet to exploit to its full potential. So let's suppose that we have dark matter, and our dark matter consists of particles with some kind of weak scale cross section for interaction with the standard model, as in many of the most attractive and popular theoretical resolutions of the dark matter problem. Now, this dark matter could potentially lose enough energy during collisions with solar nuclei to be brought below the solar escape velocity. And in that instance, it's going to become gravitationally trapped in the sun. And subsequent interactions of the dark matter with the solar nuclei could potentially provide an additional mechanism for heat transport in the sun or other stars. So if you can imagine, your dark matter particles in the center are going to absorb energy on collisions with the nuclei in the hot core, and then they're going to continue to move around and deposit it in the cooler outer layers in subsequent interactions. Now, provided that the dark matter population can accumulate to an appreciable level, so i.e. it's not going to be depleted by kind of self-annihilation, evaporation or decay, and this is what you'd expect in so-called asymmetric dark matter scenarios. This additional cooling process, which you can see here, i.e. removing the heat from the core and depositing it in the outer layers, is going to provide an additional mechanism of radial heat transport in the sun, and it's going to modify its interior properties, and these can actually be probed to high precision. So this is giving us a kind of new laboratory for searching for dark matter. And it's important to note that this approach is actually entirely complementary to terrestrial direct detection. So assuming that the dark matter in your dark matter halo is in a Maxwellian velocity distribution, it will actually be the lower velocity particles which are going to get trapped in the sun, whereas in terrestrial experiments we're most sensitive to those with higher velocities, as they're going to be the ones that produce the greatest recoils. And actually also due to kinematic matching, which tells us that the greatest momentum transfer occurs between particles of similar masses, in the sun we're going to be most sensitive to dark matter of masses around like 1 GeV, like the mass of hydrogen. So again, we're going to be probing a complementary part of parameter space to what we look at in direct detection. So how does this allow us to get a handle on what dark matter is? So if this process is occurring in the sun or other stars, and it is occurring to an appreciable level, then the change in radial heat transport is going to modify your temperature profile. And then we've got two effects. So if you've got a modified temperature profile, then you've got a modified core temperature, and that's going to really quite it's going to be your neutrino fluxes, your boron and beryllium neutrino fluxes are incredibly sensitive to the temperature profile. So any change to the neutrino flux is obviously something that we could probe. And in addition, we've also got changes to the equation of state, and that's going to change your density and profiles, and therefore that will actually modify a number of internal observables, such as the depth of your convective boundary, and the surface helium abundance. So actually there are a number of different ways which dark matter conducting energy in sun and stars can lead to observational changes. And I should say that these changes to the convective zone boundary and the surface helium abundance, they're all actually probed to very, very high precision with helioseismology. So that's how we can get a handle on it experimentally. Just another quick thing just to chuck in there is that actually standard models of the sun, our standard solar models, are actually currently in 4 to 5 sigma discrepancy with helioseismological observables. And actually it could well be that invoking this additional method of heat transport could actually provide a resolution to this problem. And this is something which has been studied by astrophysicists for quite some time, and despite a lot of effort is yet to be resolved. So actually dark matter could actually help solve a problem in astrophysics as well. So how exactly do we use this? Well, in order to make predictions of the observables and potentially put bounds on dark matter, we need to include this transport in evolutionary solar simulations. Now, the thermal behavior of a captured dark matter population will actually be fully characterized by the dark matter number density and its luminosity profile. And both of these are formally governed by the phase space distribution, which is formally governed by this Boltzmann collision equation. Now, this equation is an absolute nightmare to try and solve. It's a 6-dimensional integral differential equation, which is not in general analytically tractable. And if you wanted to include the exact solutions to this in your simulation, you'd actually need to solve this self-consistently at every time step in your stellar evolution, which, as you can see, is not going to be very, very practical at all. So what we require is some kind of quantitative parameterization of the thermal behavior of a given dark matter population that will allow us to include it easily and simply in our solar simulations, in standard solar models, and predict the observables. Sorry. So in order to be able to do this, the kind of one way of thinking about it is to think about how dark matter actually behaves. And it turns out that dark matter energy transport is actually broadly divided into 2 regimes. And it can be conveniently and is conventionally described by this so-called Knudsen number. And the Knudsen number is just the ratio of your mean free path, which is, of course, inversely proportional to your cross-section. And this parameter r chi, which is just the approximate scale height of the dark matter distribution inside your star. Okay, so if k is low, so that would mean that the interactions are strong. Now, in this instance, your dark matter particles are going to be very efficient at picking up and depositing energy, but they're not going to be able to move that energy very far. So in this instance, your dark matter will actually be in local thermal equilibrium with your solar nuclei. Now, in the opposing regime at high K, the scale over which your transport is taking place is longer because we've got weaker interactions. But now your efficiency is inhibited by your low collision frequencies. And in this instance, the dark matter is going to assume a kind of approximate isothermal distribution. So just to illustrate this, we've got two separate regimes. We've got this LTE conduction regime for low K, and then we've got the isothermal regime at high K. And we can actually see that the peak of energy transport occurs at what is termed the so-called Knudsen transition, which occurs at about 10 to the minus 36 centimeters squared for cross sections of 10 to the minus 36 centimeters squared, sorry. And it turns out that actually approximate solutions in both of these regimes to the Boltzmann collision equation can actually be found. So in the LTE conduction regime, you can solve the Boltzmann collision equation perturbatively using a first order dipole expansion. And this was first performed by Golden-Rafelt in the 80s. And you can also solve it in the isothermal regime as well, because in this case, your dark matter is just at a single temperature. Now, although we've got these approximate analytical solutions in these two extreme cases, it turns out that the only way to get a handle on this Knudsen transition, which is of course where the optimal transport occurs, is going to be numerically via a direct simulation. Now, to date, only one such study of this has been done. And again, it was done by Gold and Rafel, and this really gave people the first handle on this Knudsen transition regime. However, their simulations, although pretty seminal and although incredibly useful and gave us the real first window into this process, I should probably note that they were done for a highly simplified model of the sun. So it was a toy model. And also they only looked specifically at constant interactions between dark matter particles in the standard model. So interactions that don't depend on momentum or velocity. However, ideally, we would like to be able to generalize our results and see whether we can consider more theoretically motivated dependencies as well. So there are two existing formalisms that are used to try and characterize our thermal behavior across all regimes in one go. And first on the block, we have the Spergel and Press approximation, which basically just says, no matter what your K is, just take the isothermal solution and use that. So clearly this is only going to be actually valid in one regime, but it turns out that it's numerically stable. So it's quite simple to include in your solar simulation model. So that's why this one is still used. And the other method is kind of the standard correct approach in literature. And what they do is they take the LTE solutions, so this perturbative dipole expansion, and actually they correct them at high K. So they correct them in the isothermal regime by fitting what's known as a Knudsen correction factor which were fitted directly from these simulations. So these simulations, which were first performed 30 years ago, really have been absolutely crucial in allowing us to calibrate these two models and see whether they work. So essentially, although this is all great, we want to know how well these two approximations actually hold up in more realistic models of the sun and stars, and whether they actually can be generalized to more general types of interaction. So to this end, we've actually constructed a direct simulation, a direct Monte Carlo simulation of this. And for the first time, we're using a realistic model of the sun. And essentially what we do is we simulate chains of 10 to 100 million dark matter nucleus collisions and keep track of the dark matter position, speed, and energy transfer at each interaction point. We repeat this over a variety of different interaction strengths in order to sample each part of that curve, that K curve that we were looking at earlier. And we also repeat this for a variety of different interaction scenarios. So namely, interactions which depend on the relative velocity of your dark matter and standard model particles, and also those which depend on the momentum transfer. So what did we find? Well, after billions and billions and billions of CPU hours, we got out the following distributions. So this is just looking at constant interactions. So what did we find? We found in the LTE regime at low K, you can see that actually the Golden-Rafelt prediction works very, very well, which is as expected, because that's where the LTE regime, the Golden-Rafelt formalism is for the LTE regime. And we find that the Spergel and Press, which is shown in orange here, is actually like tremendously wrong compared to our Monte Carlo in green. In the opposing regime, we find that the Spergel and Press framework actually has a better shape compared to the actual direct true results, the Monte Carlo results. However, it's off by a factor of 2. And this was a result which Golden-Rafelt also found when they did their simulation. But the Golden-Rafelt formalisms of the standard correct formalism actually doesn't work too, it's not too bad here either. And this is all thanks to that Knudsen correction factor, which came from those direct simulations. But what happens when we try and generalize to non-constant interactions? Well, unfortunately, all hell breaks loose. And as you can see, neither the Golden-Rafelt or the Spergel and Press approximation describe the behavior of different interactions at all. So what we've got here in these plots are just various different interaction types and strengths, and as you can see, there's huge discrepancies in every case. So unfortunately, whilst these two formalisms appear to have some use for constant interactions, we can see that actually they're of little use in trying to describe non-constant interactions, which are obviously something that we'd like to be able to consider. So where do we go from this? Well, what have we found? Well, just to conclude, we found that the Spergel and Press had a much better shape than the Golden-Rafelt. But we found that Golden-Rafelt was off by several orders of magnitude for non-constant interactions. But remember that it does work well for the constant interactions. Now, it turns out if I go back to these plots, you can actually see that the Spergel and Press result actually works well in the isothermal regime. It actually fits the result very well, apart from the fact it's off by this mysterious factor of 2. So the shape of the Spergel and Press actually works well in the isothermal regime, actually for all types of interaction. So as a result, we just thought, well, why don't we just take the Spergel and Press scheme? But actually, in the same way that the Golden-Rafelt formalism corrects the LTE regime at high K, why don't we just take the Spergel and Press as like our baseline formalism and then correct this for small k? So we want some kind of way of, at small k, making the graph turn back over again. And in fact, turns out just by fitting directly to our simulation results, we find that by using the following universal fitting factor, by multiplying that by the Spergel and Press formalism, so just the isothermal case, also including this factor of 2, it turns out you actually get something which works across all interaction regimes for constant cross sections. So again, this is just showing you constant cross sections. You can see at any k, actually we've now got our new result, our new scheme in blue is actually doing an even better job than the modified Golden-Rafelt result. So that's all good, looking good for constant cross sections. But in addition, when you go to non-constant cross sections, we actually also find that across all regimes, we've now got something which actually seems to fit the Monte Carlo data very, very well. So we've actually managed to find a universal fitting formula which can be used to describe dark matter interactions across all possible interaction regimes and across each of the different interaction types that we considered. And just to hammer that really home, what I'm plotting here is just the peak luminosity for a variety of different interaction strengths for every different regime that we considered. And you can actually see that the predictions from our new scheme, which are shown by the solid lines, actually describe the Monte Carlo data surprisingly well. So I think I'm probably running out of time. So with this formulation, it's now going to be possible for the very first time to accurately include velocity and momentum dependent dark matter energy transport into evolutionary solar simulations and obtain predictions for our helioseismological observables and neutrino fluxes. And if we then take these predictions and compare them, obviously, to predictions for a given dark matter model with obviously your high precision experimental measurements, this is going to allow you to hopefully obtain some new improved bounds on the much longed for properties of dark matter, bringing us hopefully one step closer to solving the dark matter puzzle. So thanks very much, everyone, for listening, and do let me know if you've got any questions at all. Thanks.
Thank you very much for this interesting talk on this interesting topic. Okay. Please, Rebecca.
Yeah, thanks Hannah for the talk. This is a super interesting work and a really great talk. So I have a couple of questions. So first of all, I was wondering about the difference between the Golden-Rafelt formalism and what you're doing with the constant cross sections just in the LTE regime. So as far as I understand, is the main difference what you have there is just the way you're modeling the sun? Because from memory, I thought in Golden-Rafelt, they also do like a Brownian motion walk when they solve their alpha. So yeah. That's the key difference for the constant cross section?
In terms of the simulation, yes. So we did actually do the same setup as Golden Rafelt and do exactly the same parameters, and we matched their results surprisingly well. Well, I guess not surprisingly, but we did manage to replicate their results. But this random walk for these realistic models is literally just using the realistic temperature and profile models for the sun in terms of the constant interaction. I think the only other difference is they considered a sun of infinite kind of it had an infinite radius, as it were, whereas we're explicitly considering dark matter to be constrained to a finite radius sun, and we're also taking into account the fact that dark matter particles may actually get scattered out of the sun and then move on Keplerian orbits and then re-enter. So we are doing it slightly differently, but actually that makes very little effect. But yeah, essentially it's the same random walk process that we're simulating.
Okay, and so you said you put in like proper profiles, or proper like more accurate profiles for the sun. Do you remember how it was modeled in Gould and Rafelt? So it's not like the usual profile you expect. Was it based on some other power? Was it very different?
Yeah, so Gould and Rafelt used a linear temperature gradient, sorry. And they assumed a constant density of scatterers throughout the sun, whereas here we're using the density of scatterers that we set is obviously dependent on the density. We're only considering spin dependent results here, so we're only looking at hydrogen scattering. So we're using the density of our scatterers is just the hydrogen density profile of the sun from a standard solar model, and the temperature profile is the standard temperature scenario. Also, Gould and Rafelt used a kind of simplified set of units. So they were using everything was kind of scaled according to a scale length. So the temperature was essentially 1 Kelvin in the sun on average. And yeah, it was this kind of
I see. So are you saying about the density? So they were assuming constant density, so constant distribution of the solar matter?
Yeah.
Okay, that's clear. And then I'm sorry not to ask too many questions, just one other quick question. So when you were talking about, with the way I thought I understood the Gould and Rafelt formalism was that they're taking, in that particular paper, they're going through a formalism for the LTE, and they link that towards the end to the weakly interacting regime, so like the isothermal. So I thought that how that works, so you mentioned that there's a correction factor to LTE to go into the isothermal regime. But I thought that the way that worked was that like there's a function that's like a step function that just switches between strong interactions and weak interactions. Is that not actually right?
Not quite. So what they do is they take it's kind of like a step function, but basically let me just try and get up the plot. So essentially they basically base it on the LTE limit. And then the number density, as you said, is kind of taken to be some combination of the two based on parameterized by the number k. The luminosity is actually taken to be the luminosity profile that you'd expect for an LTE regime, and then you literally multiply that by a k dependent factor and also an r dependent factor. So you're modifying both the radial profile and also you're modifying it as a function of k. So there are two separate correction factors that go in, and both of those were found from the simulations. But essentially, yeah, it is the number density is, as you say, it's taking these two solutions and trying to join them. But the luminosity is actually parameterized by the LTE luminosity, but then modified by these two k-dependent and r-dependent factors.
Yeah, got it. Perfect. I was thinking about just the number density, but you're definitely right. For the luminosity, it's not quite like that. Yeah. Thanks so much.
No, thank you for questions.
There is another question by Andrea that brought me in.
Yeah, I cannot raise my hand, but thanks, Hannah. The talk was wonderful, and I really like also the idea in general. So I have a couple of questions actually. So the first one is like practically speaking, because I'm doing similar simulations for other stuff. Practically speaking, how do you treat the gravitational interaction? Because you have a profile of density, so it's not it will vary because you have to take into account the fact that you're, I mean, you are within the density, right? So it's kind of tricky. So how do you do that?
So we actually use
the full
simple harmonic oscillator potential. We don't use we don't treat.
Oh, I see.
We just use a simple harmonic oscillator potential with.
So you don't use a density, so you don't integrate to get the potential every time. You just
I think computationally that would be a step too far. I mean, this was billions of CPU hours already, but it would be.
No, I know. In fact, this is why I was asking.
To then consider what would happen if you do actually use a more realistic gravitational potential, but actually for the situation of the sun, actually the gravitational potential is well characterized by a simple harmonic oscillator in this instance as well.
Okay, and then another quick one that is like, because you have the advantage that you're doing the simulation and you really track the scattering, right? So you can track both. You talk about energy transfer, right? But you can also track the momentum transfer, right? I guess. And one that you get that you track the moment, if you have momentum transfer, then you will also have angular momentum transfer, right? Is that possible within your simulation to have an idea if you can also kind of like transfer angular momentum, and how would you do that? Because it is interesting for other things that I'm doing, or if you thought about that, because when you study flight,
it's not something I didn't actually track angular momentum transfer, but it's certainly something that you could do. So essentially what I did at every point was just save the velocity and the energy transfer, the velocity before, the velocity after, the energy transfer. But you could essentially, at all those points, you actually got the data saved to calculate the angular momentum of a dark matter particle before and after a collision. So it would certainly be possible to then build up a distribution of angular momentum transfer and then study that in different interaction regimes.
That's wonderful. Thanks.
All right.
There's one further question by Rebecca, please.
Hi, yes, sorry, I have a follow-up question based on what you were just discussing. So part of what I'm a bit confused about, so if there's this simple harmonic oscillator potential for gravity, and then the density is constant, maybe this is exactly what you were actually just saying. Why does the density then not follow the gravitational potential? Like this is just considered to be independent in the Gould-Rafelt formalism?
No, so in general, in our formalism and their formalism, well, okay, in their formalism, they have constant density of scatterers, which are set to the same density that you put into this simple harmonic oscillator potential.
I see.
In our formalism, it's kind of two separate things. So the evolution between time steps is controlled by the gravitational potential, which we just set to be the density at the core of the sun, because obviously dark matter is going to be confined to the core. However, in terms of thinking about the interaction probabilities with the different scatterers, we set those to have we set the scatterers to have the density of hydrogen within the sun, which is a realistic profile. So we're considering the density of scatterers as obviously decreasing as you go outwards, but the evolution, what governs your trajectory between time steps is set by this constant gravitational potential.
Okay, yeah, got it. Thank you.
Thanks.
There is a question by Thomas.
Yeah, thank you for your nice presentation and interesting topic. I just read billions of CPU hours later. I mean, how much computer time do you actually need? I mean, we are doing very expensive computer simulations for running 3D supernova problems, but billions of CPU hours, that is something.
Well, actually to do a single simulation, it's not that computationally expensive. However, we wanted to obviously consider several different interaction regimes. Oh, let me just see. So we are considering, let me just show you. So each point here is a dedicated simulation of sort of 10 to the 8 collisions. So you can see we've got 10 to the 8 collisions, and we've done it for, for each type of interaction, we've done it about 10 times. And we've got different different interactions as well. So that's like 60 times 10 to the 8 direct collisions. So, but each like individual dot is not too bad. It's just like the whole putting them all together is
yeah, still I mean, I still want to understand it. Sorry for being a bit insistent, because I mean, we do really big computations, and when we apply for computer time, which we need to do because the local facilities don't provide, even getting 100 million core hours is meanwhile very difficult, because we compete with a lot of groups who have demands for cosmology, for neutron star mergers. So where actually do you get billions of computer time hours? I'm getting jealous.
No, probably billions of CPU hours is probably a slight exaggeration. But I do have to thank the high performance computing cluster at Imperial College for their generous loan of their machines in this case. But yeah, no, it definitely wasn't billions. I think it was just the fact that we did so many simulations, and we obviously had to, as we refined our models, we were repeating them and doing them over and over again.
Mm-hmm. Okay. I wonder, I mean, it's in Edinburgh, as you say. I know the facility there, but and I also know the discussions which we had at PRACE meetings years ago, where it was very difficult to get computing resources for small computations, but many runs of that sort instead of few very big applications. These supercomputing facilities like the super big applications which use a lot of parallel capability of the machines, but they are not so fond of getting many small jobs to be processed. But you seem to have a good connection to them.
Well, we were very fortunate, but yeah, we did run these as like kind of we ran them on a batch process, and so we actually I didn't consider, for example, 10 to the 8 collisions in one go. I'd do 10,000 in one go and then string them all together at the end, which was obviously a lot quicker to run.
Yeah, because of my jealousy, I think I have to look out for these resources, whether we can also tap some of these many flops which seem to be available there.
You just don't know the right people, Thomas.
Thank you.
So if there is no further question or comment, I would ask Minds to stop the recording.